Hello! All right, let's get coding. In Deno, I'm pretty excited. All right, so first things first. Let's do something basic to get familiar with how things work in Deno. Let's start by learning how to work with files. And I promise we'll move to something really exciting soon. Okay, so let's start by creating a file to load. We'll call this hello.txt here. All right. And we'll write a message to ourselves. Hello, world. And we'll save it. And now we want to create a file that Deno can run to open the contents of this file and print them out to us. So we'll make a TypeScript file called mod.ts here. And I'll get to the naming of this in just a second. Okay, so what are we trying to do here? We want to create a function that reads our file. So let's call it readFile. And this looks just like any other JavaScript or TypeScript function. And at some point, we're going to call this file. All right. And now we want to open that file and output its contents. But I don't actually know how to work with files in Deno. What do I do? All right, no worries. That's why Deno has this amazing site. And part of this site is this runtime API page, which lists all of the functions that Deno makes available out of the box. That is, these are all of the functions that we can use without importing them explicitly. So let's take a look at what we have here. All right, I'm already seeing deno.open, deno.openSync, read, and a whole bunch of file-related functions. So let's take a look at deno.open. Okay, so it takes a path and some options, which we can see here in the sample code, can specify whether the file is readable and whether the file is writable. And we're also seeing that we should be closing these files when we're done working with them. But let's see if there's something that helps us a little more explicitly. So we have this read function here. And all right, it looks like this function will give us a bunch of bytes that we can then decode with a text decoder. That seems a little bit complicated. Let's look a little further. Okay, so I'm seeing a function called readTextFile here. Now, this seems like it does exactly what we need. And there's no need to actually even call that deno.open function. Deno is actually making our life really easy here. There's a lot of really cool and useful convenience functions that it makes available out of the box that a lot of other runtimes don't have. Okay, so we're going to actually copy this example line here into our function. And we're going to make sure that the file name matches our own. And then all we want to do is we want to output that data so we can use this console.log that we're probably familiar with from programming in the browser. And this is actually available to us in Deno, just like it is in Node. But it sort of underlines this philosophy that Deno has, which is to stay aligned with the browser APIs as closely as possible. So we'll actually see this some more in examples like the fetch function or web workers. But let's get to that in just a bit. So let's run our program. We'll be using Deno to run our file, which we called mod.ts. And let's see what happens when we try to make this happen. All right, so Deno tried to compile our file, and we got this error here. Await expressions are only allowed within async functions and at the top level of modules. That's actually a pretty useful error. All right, thanks, Deno. So what we need to do is we need to make our function async. And then when we call it, we need to call await. Okay, let's try to run this again. Okay, so Deno tried to compile our file again, and we got another error. This time it's permission denied. Read access to our file was denied. We need to run it again with the allow read flag. Now, this is when those permissions that we talked about earlier is coming into play. Because we're trying to read this file from our hard drive, we need to pass in this flag before we can run it. So we'll do that now. Allow read. All right, and third try's the charm, right? Let's see what happens. Hello world, yes, all right. Okay, now that we've celebrated, let's take a moment to dive a little deeper into our little Deno application and see what Deno does for us. Remember these two really useful functions that we saw? Read text file and read text file sync. Deno provides the asynchronous version of this function, which we can see returns a promise, and the synchronous version of this function, which has no need for a promise. The main difference being that with the synchronous function, the program waits until the file has been read and all the data is available to us before continuing. Whereas with the asynchronous function, Deno can actually switch contexts and run some other code, if there's some available, while it waits for the file to be opened and read and processed and all of that. The main thing to note here is that Deno provides a modern TypeScript API that leverages all of the modern JavaScript and TypeScript features that we want to use today. A lot has changed in JavaScript over the past 10 or so years, and we really want to make use of all of those improvements that have been made. Okay. In this course, we're using VS Code, and with the VS Code Deno extension, we don't even need to load the documentation in the browser. I can just hover over this function, and I'll get the exact same information that was available to me in the previous documentation, right in our editor. So you can pick which option you prefer. Another cool feature of TypeScript that we can use is this top-level async await. Remember that error we saw? Notice that normally we would need to use this await feature inside of an async function. But because it's such a common use case to await something at the top level of a file, TypeScript provides functionality for us to do that. We don't have to wrap this call inside of a function or inside of a promise. To compare with Node, top-level await was only introduced in Node in version 14, and even then, only under certain conditions. With Deno and TypeScript, we get this behavior out of the box. We didn't even need to worry about it when writing our little application. But now you know. Let's look at how importing modules works in Deno. We're going to improve our read file function a little bit. So remember this hello.txt file with our funny text? Say this file were in a different directory. So say text_files, and we moved hello.txt into our new directory. How would we load it now? You might say something like, let's put the directory name in front of the file name. So text_files/hello.txt. Now, that might work, but you might also know that file paths look differently on different operating systems. So on Windows, a file path that looks like C/Windows/system32 might look like /user/bin on OS X or Linux. Notice the backslash versus the / here. These two paths are actually incompatible. The good news is that Deno actually has a function that will handle this difference for us, so our code will work on any operating system, whether that's macOS, Linux, or Windows. To use this function, let's import our first module. So we're going to use an import statement, and we're going to import this join function from a module. And we're going to reference this module directly by its URL. So in this case, it's going to be HTTPS, and then our favorite site in the world, deno.land, /std/path/mod.ts. This is pointing to the standard library provided to us by the Deno authors, which includes many of the functions we'll be using throughout the course. From dealing with file paths, to dealing with logging, to dealing with HTTP, this standard library has a lot of functions that we're going to be coming back to throughout the course. So let's put our new import to use. We're going to create a new variable to hold the path to our file. And we're going to create this path not by hard coding it as we have here, but by using this join function. And we're going to call this join function with all of the different pieces of our file path. So text files, the name of our directory, and then hello.txt. Now that we have this path, which uses the correct operating system specific path format, we can pass it in to our read text file function. And let's see what happens when we run this. Our little app still works. And now we can run it on different operating systems. That's a big win in my book. Okay, but remember that mod.ts file that we named? Why did we name it that way? And why did our import have its own mod.ts file? So Deno doesn't believe in any special file names. You might know index.js from node.js, which had all kinds of special meanings, from being the default file that Node runs to being the file that is imported when you try to import a directory. Deno, on the other hand, is all about simplicity and flexibility. We don't have to keep track of any such special cases. The mod.ts file name here is just a convention that Deno module authors use to let developers know that this is the likely natural entry point of the application. That is, this will usually be the file that you import from a module, as we see here, or that you run in an application, as you see here. This convention actually comes from Rust, which is the language that Deno is written in. But Deno assigns no special behavior to mod.ts. It's just a file name we'll see a lot, and one we'll get comfortable with as we become experts in Deno. All right, now we're getting to the good part. We're going to be building something from what we just learned that I'm personally super excited about. Why? Well, we're going to be exploring space, planets beyond our solar system, and finding those planets that are most likely to be habitable. That is, planets that humans could one day live on, or even potentially planets that might already support alien life. And we're going to be doing all of this using Deno. The story starts with the Kepler Space Telescope. This was a state-of-the-art telescope launched into space in 2009. For nearly 10 years, it looked out into space and gathered data about planets beyond our solar system. Kepler observed hundreds of thousands of stars, and in doing so, discovered over 2,000 planets. And the best part? NASA shared all of the data that Kepler gathered, which means we're going to take a look. All right, but how are we going to do this? Those of you who were particularly observant will have noticed that the directory of the basic file app that we built was called CSV-example. So what's the CSV part? Well, we're going to be getting our data from the NASA Exoplanet Archive. And you might be asking yourself, why exoplanet? Exoplanets are just planets that live outside our solar system. They orbit other stars, other than our own sun. And we're going to download the table of all the data that Kepler gathered in CSV format. So we're going to download the table, and we're going to save it to our example directory here. Okay, so what is a CSV file? Well, CSV stands for comma-separated values. Let's see what that looks like. So we have a header here, which is a comment, and this says this file was produced by the NASA Exoplanet Archive, which we just visited. And then it's followed by a listing of all the columns in this data file, which have pieces of data such as the name of the planet, the orbital period of the planet in days, even things like the radius of the planet. And then there's also some interesting information here around the star which the planet orbits. So the effective temperature in Kelvin of that star, or the mass, or even the age of that star. This is all data that we can explore. All right, so scrolling down through all of these comments, we see that the next line is this header of our CSV file, which contains a list of all of the column names that we were just going over. And it's followed by a list of all of the data. And we can see that the data includes a few different data types. So we have numbers and we have strings. And the key here, because this is a comma-separated value file, all of these data points are separated by commas. So each row is separated by a comma. And you can see that this file actually has thousands and thousands of different potential planets that were discovered by Kepler. In fact, there's 9,650 of them. So now that we know what we're working with, let's get started exploring this data with Deno. Let's get exploring. Remember how for text files, we had a convenient function that pretty much did all the work for us? If we look through the functions in the Deno runtime docs, there's really no such function for CSV files. Okay, we're going to have to get our hands a little dirtier this time. We're going to have to start by using this deno.open function. Okay, so we're going to change our call to the readTextFile function to deno.open. We're going to change the path to our file to our current directory and the name of our Kepler exoplanets data file. And while we're at it, let's rename our function to, let's say, load planets data. Our next step is going to be to import another module. So we're going to import this buff reader from deno.land and still our standard library, but this time the IO module and the buff.io.ts file. You might be asking, what is this URL and how do I find out what this buffered reader does? If we go back to our favorite Deno.land site, we can see that there's this standard library documentation. And if we scroll down to the IO module and click on the mod.ts file that we talked about earlier, we can actually see a link to view the documentation for this module. Let's check it out. All right, so if we scroll down, we can see this buffReader class. And we can see that buffReader implements buffering for a reader object. So what's buffering? Buffering is just holding on to the data for a little bit before using it. So instead of sending data back byte by byte as it's being read, we send back, for example, a whole line of data at a time. And this is a fairly common thing in programming that you might have seen in other programming languages. If we think about it for a second, how useful is just one character of a string? Or just one pixel of an image? We generally need larger chunks of data to make sense of. And we can also see that there's a bunch of methods that this class supports. So we can set the size of the buffer. We can read from it. We can even read a whole line from it. So this is good to know, but it turns out we're not going to be the ones who are actually consuming this buffer. So let's get back to our code. We're just going to create a new buffered reader. From our file. And we're going to use another library to consume this buffered reader and parse our CSV. And before we do that, let's make sure to rename this data variable to file. Okay, so we're going to import this parse function from deno.land/std. And then there's this encoding module with a CSV file. And we're going to use this parse function to parse our buffered reader. So let's take a look at this module in the standard library documentation. We can see that this parse function takes an input, which is our buffered reader, and options, which are defined as this parse options object. And this parse options object supports a header field and a parse field, but we can also see that it extends this read options object, or this read options interface. So if we click on that, we can see that it supports those two properties, but also all of the properties from read options. So we can also see that there's this comment property, which specifies the character to start a comment. So if we go back to our code and look back at our CSV file, we can see that we have comments that start with this hashtag. And we can also see that we have a header with the labels for all of our different properties in our CSV file. So we're going to set those two options on our parse function. So we're going to say header is true. We want it to parse that header and not treat that as a line of data. And we're going to say the comment is the hashtag. Okay. And we're going to set the result of this parse to a result variable. And let's console.log that result. If we think back to when we looked at the deno.option documentation, remember we saw this deno.close? We want to make sure that we close the resource that we just opened so we don't end up with a memory leak. So we're going to do that. We're going to deno.close the resource ID for our CSV file right after we're done parsing it. Okay, let's run our application. So we're going to do Deno run, and we still need to pass this allow read flag because we're still reading our CSV file. And we're going to pass in mod.ts. All right, so it looks like Deno has read a whole lot of data from our exported data. If we scroll up a little bit, we can see that all of the rows in our CSV file have been exported as objects. And the other thing to note here is that all of the data is being returned as a string. All right, so we've successfully imported the data from the Kepler Space Telescope. And now we can start exploring this data. Very cool. Welcome back. Let's find some Earth-like planets that might support life beyond our solar system. So, at a high level, we're going to want to filter through all these planets that Kepler found. And we're going to be looking for specific properties. So let's start by changing our function here to return this result. Our goal is going to be able to get this list and, for example, count the amount of habitable Earth-like planets that we find in it. So we're going to do something like assign this to a variable, and let's call it new Earths. And then we're going to log the amount of planets that we find. So we're going to do console.log. And then let's use this template string, new Earths.length. And that's the amount of habitable planets that we found. Okay, so now we have a list of all the Kepler exoplanets here, including unconfirmed ones. So we're going to write a filter on our result array right after we close the file here. And we're going to assign this to a new variable. So we're going to say planets equals result dot filter. And each piece of the result that we're going to be filtering through is a planet. We're going to be looking for something in these planets. So we're going to start out by looking back into the CSV file and taking this disposition field here, which just means the current status of the planet. If we scroll down here, confirmed, or it can be just a candidate, or even a false positive. So we want to filter out only the planets where the disposition, so we're going to take this field name, koi disposition, and we're going to match it to confirmed. Perfect. So now we're only matching those results that have been confirmed as planets. Next, the Habitable Exoplanets catalog has done some research and found that the radius of the planet should likely be between half and 1.5 times the radius of the Earth. And that's to maximize the chances of a rocky surface with liquid water, similar to that which we have here on Earth. Okay, so we're going to look for this property here. And we can find, okay, so here we have planetary radius in Earth radii. Perfect, so we're going to take that. And why don't we assign it to a variable? So we're going to say planetary radius equals planet, and then take this parameter. And then in our check here, in our filter, the planet needs to be confirmed, but it also needs to have a planetary radius between half that of Earth and 1.5 times that of Earth. Okay, so we're starting to build up some confidence on the habitability of these planets that we're finding. We're going to look through one more piece of data. The Journal of Astrobiology published some research, some findings in 2017. The highest confidence of intelligent life exists on planets orbiting stars whose mass is between 78% and 104% of the Earth. So we're going to be looking for the star's mass in our CSV file. Okay, let's see. I remember seeing a bunch of stellar properties here. Yep. So we have stellar mass. And we're going to take this and add it to our filter. So let's create a stellar mass. And we're going to assign it to this property in our CSV file. And we're going to check for exactly those conditions. So it's going to be stellar mass. And let's just double check here. So it was 78% and 104%. So 78% and stellar mass needs to be less than 104%. Okay, and finally, we're going to narrow the results even further by looking for a planet who's orbiting a star that's so similar to our sun that we have that extra confidence. So I'm going to take this stellar radius parameter here, and I'm going to make a really tight range for this to be in. So it's going to be stellar radius, and it's going to be this property. And stellar radius needs to be greater than 99% of the sun's, but less than 101%. So we're being super narrow here. All right, so that was a lot of science and math. I hope you find this as fascinating as I do. We can do real research on our universe in much the same way that we're doing right now in Deno. Okay, so what's this red underline here? Okay, so TypeScript is telling us that object is of type unknown. Looks like we're going to have to flex our TypeScript muscles here a little bit. TypeScript is telling us that this planet here is of type unknown. So what we're going to do is we're going to define a TypeScript interface. So we're going to say interface planet. And this is going to help us shape the data that's being returned. Remember, one of the powerful tools that Deno gives us over other runtimes is type safety. So it's worth taking advantage of. So what we're going to do is we're going to say that each of these planet objects is going to have a key that is a string. So what we're saying is that these planets can be indexed, right, using these square brackets with anything that's a string. And then the second part here is that we're saying that the value at that index, the value with that key, is a string as well. Remember that unknown we saw here in this planet? Well, this is coming from this result object, or this result array. This promise, this parse promise, is, as you can see here, resolving to an array of unknowns. So what we're going to do is we're going to say this result as array of planets. This is called a type assertion in TypeScript. We're telling TypeScript, trust me, this unknown type here is actually a planet array, and we should treat it as such. Okay, so now you can see that TypeScript is no longer complaining, and it knows that this object is a planet. But look, there's another error. TypeScript is now telling us that comparison operator here can't be applied to types string and number. Right, because remember how our CSV, when we were parsing it, returned the values as strings, even if they were just numbers? So we're actually comparing strings to numbers here for each of these properties. This type assertion that we just did helped us detect that otherwise we'd be comparing a string to a number. something we might do completely unaware in JavaScript. So we can be safe and use this number constructor on each of these properties to ensure that they are indeed numbers. And look at that, no more errors. Okay, let's run this scientific marvel that we've created and see how many new Earths we've found. So we're going to do Deno run. Okay, moment of truth. Whoa, 9,000 habitable planets found. Looks like we're not doing something right. That's all of the planets in the Kepler list. Okay, so we need to change this result to return the list of planets. Okay, second try's the charm. 8 habitable planets found. Not bad. That's a lot of new Earths for us to explore. Awesome. Okay, in the next video, we're going to examine the data from the planets we found. See you soon. In this video, we're going to open up a whole new world, a new, fantastic point of view. Deno can run a whole lot more code than you might have ever thought possible. Back to our project. We've found some habitable planets that we'd like to explore. Let's dig a little deeper. We can start by printing all of the information on the planets that we found. So we're going to use a for const planet of new Earths. And we're going to just console.log all of these planets. Here we're essentially iterating over all of the values of this array. That's what the for of statement does. So let's give this a run. And you can see that a whole lot of data on each of these planets is being returned. In this case, we're only really interested in the data that we're filtering by, and maybe a few extra pieces of information. So what if we wanted to only filter certain keys from all of these objects? This is usually a common use case for a JavaScript utility library, like Lodash. Lodash is a very popular JavaScript utility library with many helper functions that you've probably heard of. And it's for working with things like JavaScript objects and arrays. Can we use it in Deno? Deno takes JavaScript and TypeScript files and imports them as modules. And we know that Lodash is JavaScript, right? But does it export itself as an ECMAScript module? This is basically the modern JavaScript specification. And the answer to our question is yes. If we check the release tags, we can see that one of the releases for each version of Lodash that's released is this ES version. This is the version that exports itself as an ECMAScript module. Because Deno supports importing ECMAScript modules, we can use this extremely useful library. So let's grab the main file from the latest version of the repository, and we're going to search for lodash.js and import the raw version of this source code. So then going back to our code, we can do an import of everything in this library as underscore, which you've probably seen if you've used either underscore or Lodash before. And then we're going to copy this URL from GitHub. And the function that we're going to use from Lodash is this pick utility. So this creates an object composed of the picked object properties, which basically means that it filters out only the keys that we care about. Okay, so what we're going to do is, for our planets, we're going to map over all of them. And we're going to return the picked version of that planet. So the version with only the keys that we care about. So in this case, we're going to copy the ones that we know. So the planetary radius, the mass, radius, and then there's going to be a few more. So let's grab the name of the planet. And let's grab the number of planets in the system. And maybe let's finally grab the temperature of the star. Okay, and let's see if this works. So you can see Deno is now returning only those properties that we care about. And we can actually have a much better insight into what these planets are all about. For example, we can see their names. We can see their radius. And we can see that most of them only have one planet in the system. Turns out it's not very common to have all these properties that we're searching for. And most of their temperatures are close to that of our own sun, which is about 5,700 Kelvin. Okay, so we can also find Lodash on the deno.land site under the third-party modules section. So this is basically just a redirect to the very same files that we saw on GitHub. Notice the same tags. So we can grab the URL for this module and replace the GitHub URL that we were just using. And it should still work. All right, perfect. Turns out that any modern ECMAScript module, whether it's designed for the browser or for Node.js or any other runtime, can be used by Deno. That's super powerful.